Okay, if the frequency of the generated voltage is too low, maybe you measure it here or you measure it here, the frequency is too low. So what you can do is that you can increase the no load speed of the mechanical galvano. Means that the whole slope here shift upward. You shift upward. So means that at the end of your point here at full load frequency will be shifted upwards as well. Okay, active and reactive power of your generator. The power from generator can be found using the P generated is equal to speed at full load minus frequency at no load minus frequency at your system and operating system frequency. So this is your the power, the no load frequency minus your operating system frequency. Let's say your operating system is 50 Hz. So the no load frequency of your system, when you measure, so this is the power. The slope is often quoted in kilowatt hertz or megawatt per hertz. So the no load power PNL, PFL is your full load power. This is the slope of power. How much the difference of your power when at full load divided by your no load. So the effect of changes in the terminal voltage with the reactive load can be plotted in a diagram similar with the frequency power plot. We plot the kVAR here, kiloVAR, kVAR here, versus terminal voltage. So we can see that the supplied voltage with the no load compared to the full load to be reduced linearly when connected to the reactive power. And we deliver, the more the reactive power we deliver, the lower the terminal voltage will present. So the plot shows the linear reduction in voltage as the reactive power draw from the mechanical system increase. The higher the reactive power we draw, the lower the terminal voltage will be measured. So when we increase the inductive load on generator, it will reduce the terminal voltage. If we add capacitance, so it will increase terminal voltage. So inductive load will reduce the terminal voltage, meanwhile your capacitive load will increase the terminal voltage. So the reduction of the terminal voltage can be compensated by increasing the no load voltage. And same, you have to increase the no load voltage. Increase the whole graph here. Okay, as a summary, when the synchronous generator operates alone, the real reactive and the real power and reactive power supplied by generator will be amount demanded by the attached load. And the governor set point of generator will control the operating frequency of the power system. The field current of the field regulator will control the terminal voltage of the power system. So means that the load only can draw whatever the generator have, or you have to match the generator with your load. And the governor of the generator itself will control the frequency. Meanwhile, your field current is used to control your terminal voltage. Okay, in synchronous mode, you have two generators. One we put on the right side, one on the other side. So this is genset 1, this is genset 2. So this one will present the house diagram of the genset 2 to be parallel with the system. So this is the original genset. This is the incoming. And so this is incoming. Consider the case with two generators, G1 and G2, connected to supply the power requirement of the load. In this case, the frequency powerhouse diagram plots like this one. So the total power, the load is the sum of the genset 1 plus genset 2. So the total load limits or range that the generator can provide is this one. Total load is PG1 plus PG2. So PG1, this is at 60 Hz. Because we are operating at 60 Hz, so we take the 60 Hz point. 60 Hz point. So let's say we plot the genset 1. Genset 1 at no load, this is the frequency. At full load or at the system frequency, so this is the power it can deliver. And the power from 0 up to here. So this is the PG1, the generator 1 can supply. Meanwhile, for genset 2, at no load, the frequency already low, almost like that, like 61 Hz. But at frequency load, which is 60 Hz, it only can deliver a few of it, fraction of it. So this is considered as your available power of your genset 2. What happens that if you want to gain more power from your genset 2, you have to lift all together here. And lift the slope here all together upwards, such that you can extract more from the genset 2. If you maintain like this, means that only fraction of it you can gain from genset 2. And so this is the total load power of the system. Okay, active and reactive power sharing between parallel generator. So what happens here, like I told you before, if you want to gain more from the genset 2, you have to shift upward and the whole graph here, such that now you can shift the overall shape from this is initial total here, total load sharing. When we shift upward, so we can shift the rectangular shape here to the right, and so now it's here already, and means that we are able to reduce the burden on the generator 1. We put it to the generator 2. So P load will become PG1 plus PG2. Meanwhile, your generator load power is your SP times full load speed at no load, minus system speed frequency. So the total power supplied by both generator is equal to this one minus plus P genset 2. When the governor set point G2 is increased, so the governor set point here we increase, the system frequency will increase, and system frequency here, the overall system frequency will increase. The power of your genset 2 supplied by G2 is increased, while the power supplied by G1 is decreased. And instead of higher power supplied at initial condition just now, so when we increase, the governor increase the generator 2 set point, so the amount reduced, it top up to the genset 2. Okay, the effect of increasing G2 field current on the operation of the system. When we increase the field setting, so the terminal voltage of your G2 also will increase, and so the Q will increase. Total Q now will have increase on the genset 2. The system terminal voltage will increase. The reactive power Q2 supplied by genset 2 is increased. Meanwhile, the reactive power take or we absorb from the G1 can be reduced. Okay. So in terms of frequency versus real power and the terminal voltage and the reactive power characteristic of the system is constrained by the such that the total power supplied by genset 2 must be equal to the amount consumed by the load. So neither the frequency of the system nor the terminal voltage is constrained to be constant. And so we have to make sure that the frequency is to be set at the system frequency. And so means that if we want to draw more power from your genset 2, we have to set the governor such that the whole graph here of the genset 2 increase. Then the frequency will maintain. Power draw from your genset 1 will reduce. We top up to the genset 2. So to adjust the real power sharing between the two generators, we have to maintain the frequency. So steps to be taken: set the governor set point to one generator. Increase the set point. Let's say we increase the generator 2 and decrease the governor set point on the other generator. And so we play around between two generator set point. Either we increase another side, we decrease another side, so we can manipulate the shifting power sharing without affecting the system frequency. Means that this is system frequency reference, and the cross line here is the system frequency reference, which reduce or increase the set point either on the either generator with maintaining the frequency set point. So the F is constant. So the effect or the benefit is that the generator which the set point increase will handle more of the load than other. Increase more means that the P will increase more. A good power sharing between the generators should have speed droop range between 2 to 5% only, and you have to limit between 2 to 5%. If you drop more than that, so it's considered as a least perform generator. So if the load is changing, we have to adjust the reactive power Q between two generators without changing the terminal voltage of the system. If we plot in the voltage terminal versus kVR, so the terminal voltage should be constant. So we adjust the set point of the governor, but we have to maintain the terminal voltage. So generator whose the field current increase will handle more reactive power. Increase more, so reactive power will be more on that side. And if we have a load, the load is constant, we want to increase the frequency, and to adjust the frequency, so we have to increase both governor set point and increase both governor set point such that the frequency of the new frequency will meet by the both of the generator. So the power sharing is the same. P1 and P2 are the same, but only the frequency is shifted upward. Okay. So if load is constant, also to adjust the terminal voltage to another new terminal voltage, so we have to adjust shift the whole graph here of the governor upward. So increase the both generator field current or decrease both generator field current. So we have new terminal voltage when we increase or adjust the field current. So we shall discuss the example in the other slides. Thank you very much. So next we go to the synchronous motor. Okay. Synchronous motor will be on the next slide.